The content in this presentation aligns with pages 77 through 80. So it's sort of a closer up view of a topic we covered earlier, but it's meant to help you achieve learning objective 14, which is to interpret patterns depicted on world temperature maps. So if you haven't already done it, skim the pages 77 through 80 before you watch the rest of the video. We don't have any new key terms for this part of the video. But please plan to read through those pages 77 through 80 again, because there's certain parts of it that we'll want to focus on the exam. This should be a pretty quick video, but what I wanted to do with this is show you these two maps side by side, which I don't think we really get to stare at too much in your textbook. These maps are sea level temperatures in the seasonally extreme months of January and July. So on these maps, you can study global temperature patterns and the effects of the controls of temperature, especially latitude, the distribution of land and water, and ocean currents. As with most other isothermal maps of large regions, all temperatures on these world maps have been reduced to sea level to eliminate the complications caused by differences in altitude. On both maps, the isotherms generally trend east and west and show a decrease in temperatures poleward from the tropics. They illustrate one of the most fundamental aspects of world temperature distribution, that the effectiveness of incoming solar radiation in heating our surface and the atmosphere above it is largely a function of latitude. Moreover, there's a latitudinal shift of temperatures caused by the seasonal migration of the sun's vertical rays. To see this, compare the color bands by latitude on the two maps. If latitude were the only control of temperature distribution, we could end the discussion right there. But that's not the case. The added effect of differential heating of land and water is reflected on both of those maps. The warmest and coldest temperatures are found over land. Note that the coldest area is a purple oval in Siberia. So right up here. Red isn't showing up too well. The hottest areas are the deep orange ovals. So here and here. Okay. All of those are over land. Consequently, because temperatures don't fluctuate as much over water as they do over land, the north-south migration of isotherms is greater over the continents than over the oceans. Also, it's clear that the isotherms in the southern hemisphere, where there's little land and where the oceans are dominant, are much more regular than they are in the northern hemisphere, where they bend sharply northward in July and southward in January. Isotherms also reveal the presence of ocean currents. So warm ocean currents, let me get some of these arrows off of here. Warm ocean currents cause isotherms to be deflected toward the poles, whereas cold currents cause equatorward bending. The horizontal transport of water poleward warms the overlying air, and results in air temperatures that are higher than would otherwise be expected for the latitude. So we can see, for example, poleward movement of that isotherm. Here is an equatorward motion. So this one is warm, right? And it keeps Great Britain warmer than we would expect it to be at 50 degrees north. And this current bends the isotherms towards the equator, bringing cool water up the west coast of South America. These maps show the seasonal extremes of temperature, and comparing them enables us to see the annual range of temperature from place to place. So comparing the two maps shows that a station near the equator has a very small annual range because it experiences little variation in the length of daylight, and it always has a relatively high sun angle. A station in the middle latitudes, however, experiences wide variations in sun angle and length of daylight, and hence has big variations in temperature. So that means that we can state that the annual temperature range increases with an increase in latitude. Moreover, land and water also affect seasonal temperature variations, especially outside the tropics. So a continental location has to endure hotter summer and colder winter than a coastal location. Consequently, outside the tropics, the annual range increases with an increase in continentality, which is the tendency to be in the middle of a continent. The figure on this slide shows the global distribution of annual temperature ranges, and it serves to summarize the preceding two graphs. By examining this map, you can see the influence of latitude and continentality on the temperature statistic. The tropics clearly experience small annual variations, as expected, right? I see 3s and 5s and 6s. Here is the equator. We're at 3 degrees C. As expected, right? The highest values occur in the middle of the large land masses in the subpolar latitude. So here's that big purple spot on the January map for the Northern Hemisphere. And here's another bright blue or purple spot. It's also obvious, though, that the annual temperature ranges in the ocean-dominated Southern Hemisphere are much smaller than in the Northern Hemisphere with its great big continents. So use the content provided in this presentation, along with other content you find in the book and on the Canvas site, to verify that you can answer these questions for the midterm. If you can comfortably answer them, you're in great shape. If not, reread the text, rewatch the video, and see if that helps. And if you're completely stumped, start a discussion or ask me for help.